Hi. Yes, thank you for having me, and thank you for the lovely introduction. I believe you can see my screen. At least that's what Zoom is telling me. So unless I hear otherwise, I will assume it's all well. So yeah, I'm going to be. I have to add a couple of caveats first. The brief I was given is to focus on black holes and leave neutron stars to the much more qualified people that will follow after me in the sessions. And so I will mostly focus about black holes, unless your questions are probing me in those areas. The other caveat that I have to put in is I understand there is a very wide range of expertise and interests and familiarity with the topic in the audience, and so I tried to get something that had a little bit for everybody. And I apologize in advance because I realized that in doing so, that means that they are always going to be parts of the talk that will not satisfy some of you, unfortunately. So please don't hesitate to ask questions and put questions in the Q&A, because it's particularly difficult to create a talk that is both accessible to everyone and yet will satisfy some of the more technically minded audience members. And the last point that I feel like I have to mention is this is one of those Zoom presentations. I'm here in my living room talking to my screen, and I have very little ways of feedback. So if you please accept my apologies in advance if sometimes I ramble a bit. Normally I have the stern look of the front row of the audience to keep me back on track, but now here I'm a bit on my own. So without further ado, moving forward, I'm mostly going to be talking of stellar-sized black holes with the lens of gravitational waves, because that's what I do and that's my own expertise. And because I am, like most professional astrophysicists, I am hopelessly biased into thinking that what I do is the coolest thing ever. And so this is what I'm gonna be focusing on, with a little bit of introductions on black holes themselves. So to get an idea of scale, we're talking about the extreme stellar environments, and I want to give us a little bit of scale. So this is to scale a picture of the sun, ours, which is about 330,000 times the mass of the Earth. You can see the Earth, depending on the resolution of the screen you're watching this presentation in. You should be able to see the Earth as the little dot on the right. The average black hole, which we call this stellar-sized black hole, there are black holes that can be much bigger, and there are theoretically black holes that could potentially be much smaller. But the standard vanilla black holes that comes from stars would be on the order of 10 solar mass. It's more of a fiducial number than really an average number, but that's so 10 times the mass of the sun. The black hole of that mass, 10 times the mass of the sun, would actually have the diameter of 100 times smaller than the radius of the Earth. Its radius, sorry, would be 100 times smaller than the radius of the Earth. That means here on the picture, just to scale, in that little round black dot in the middle of North America, there would be the mass of 10 times of the sun. So we're talking about extremes of the universe, and arguably the ultimate possibly density. I mean, this is where most of the laws of physics go bonkers, to the point where well, we don't really know what happens inside. So first, how do we know about them? And there are several ways. This is a artistic illustrations of black holes from Sinus X1, a star, a very big giant blue star, 20 solar masses, so 20 times the mass of the sun, which is being slowly swallowed by a black hole of about 15 solar mass. The drawing is, of course, artistic and not quite fully physically accurate, but it gives you the idea The only way we know this is happening is not because we can see the black hole, but because we can see the effect of that superheated gas orbiting around the black hole and emitting those jets of radiations and matter that we can somehow detect. However, this is an example of stellar-sized black holes, and while this is an example that explains to you how we can observe and the effect they can have on the environment, and Albert Einstein's, we have to go deep into the fundamental questions of what is gravity before we can actually talk about what is a black hole. So the force of gravity is this universal attractions between anything that has a mass, the famous example of the apple being attracted by the Earth, or in our case now that we're experiencing, ourselves, persons, and the Earth, or the Earth being attracted by the sun. So this is something within this theory of gravity, where we call the Newtonian theory of gravity, where you have this attraction between any object. We can build the concept of escape velocity, the speed that a projectile needs to have to actually leave the gravitational prison, the gravitational attraction of a celestial body. On Earth, that escape velocity is 11 kilometers a second, meaning that every time we want to send a spacecraft out of the Earth influence, it needs to reach that speed. That is obviously very fast, but that's something that we can do. Not myself per se, but we, humanity, have been able to do that several times, which is still impressive in its own right. And this is for something, this is an example of the Earth. So for something with the mass of the Earth, with the radius of the Earth. What if I crank up the numbers a little bit, and now I get something the size of the sun and the diameter of the sun? For simplicity, let's just say it's the sun. The escape velocity for the sun being a lot more massive, is now 700 kilometers per second. So something, if we want to have something leave the gravitational influence of the sun and leave the solar system, now it needs to reach that speed, which is obviously quite a bit faster. Now let's start to mix things up. What if I get the mass of the sun, but I pack it into the diameter of the Earth? So something a lot denser than the sun. Now to leave that body, if I'm standing on the surface of it, I need 7,000 kilometers per second. Those numbers, roughly the size of the sun into the mass of the sun into the radius of the Earth, that's not just pure speculations. This is about the dimension and density of a white dwarf, the remnant of a star exploding that we just talked about in the previous talk. So our white dwarf living aliens need to have rockets that can go to that velocity before they can go and explore everything. But you know, we don't have to stop there. Let's instead pack the sun into a sphere of about 12 kilometers in radius. Now we need about 150,000 kilometers per second to actually escape it. Those type of dimensions are what you will find around neutron stars. So we're talking about speeds that start to be quite extreme, but as is fitting the subject of this series of talk, we are in the extremes, so we can pack things even further. And now if I pack the sun into something about 3 kilometers in diameter, now my escape velocity is about 300,000 kilometers per second. An object like this, as we just saw 2 slides ago, that's a black hole. And that speed at the bottom should be familiar to most of you. That's about roughly the speed of light in vacuum, meaning that even light cannot reach the required escape velocity to leave that object, that object that has the mass of the sun in such a small radius. So that's what we would call a black hole. It will look black to us because light cannot escape it. Ergo, it just looks black. So this is the first theoretical definitions that we can have on the black holes. However, and it is a useful description to understand some of what happens around the black hole. It is, however, not quite correct. And the fundamental mistake that I just wasted all of your time on is actually using Newton's theory of gravity to try to understand what black holes are. And Newton's law are not really applicable in the case of such strong gravity as you will find around black holes. Newton's law are very applicable and very useful in a lot of ordinary day-to-day situations for us on Earth. They are not quite accurate enough when we're talking about the type of extreme environments around black holes. As an example, in this concept of escape velocity, while the light leaving a black hole will not reach the necessary escape velocity, it's not as if it was going up, slowing down, and then the photon, the particles of light, will come back down. Around the black hole, as anywhere in the universe, light always travels at exactly the same velocity. And if you're traveling at near the speed of light and you turn on the flashlight, the light coming out of the flashlight still travels at the speed of light. Velocities don't add at those type of extreme values quite the way we intuitively have in mind. So in this case, around the black hole, just to stay and to hover just above the edge of the black hole, the edge beyond which nothing can escape, the edge beyond which you would need to go faster than the speed of light, you still need to travel at the speed of light or near the speed of light just to not fall in. So you're traveling fast, but you're actually not moving. It's one of those quirks of space and times around black hole. Speaking of which, so Newton's law in the theory of gravity as given by Newton's, space and times are unchangeable. They are just immutable, constant of nature. Gravitational force works at a distance with no delay. And while Newton's law are generally very accurate, they are not perfect. And they are actually day-to-day devices that we use, and the best example is the GPS system, which would get unusable within seconds or minutes if we were to base everything on Newton's law. So this is an example here in that little animation. We have two celestial bodies. One orbits around the other just because it has this gravitational force represented by the red arrow that keeps pulling it towards the center. Where does this arrow come from? What is the force? How come it's instantaneous? What is actually the reason of that force? None of that is touched on in that theory. It just is. You have the formula, you compute things, and you can predict how certain things work. In Einstein's theory of gravity, things are a little bit different. Space and time are actually two facets of the same thing, and they are bent together in this construct that we call space-time. For instance, the circumference of a circle might not necessarily be 2 pi of the radius. And here in the video, this is the example where now the mass of the heavy celestial body in yellow actually creates a dip in this fabric of space-time. And what makes the small body actually orbit is just that it's constantly falling. There is no friction in space, so it just keeps orbiting, but very much like a pebble in a sink will just keep rotating around. As long as it maintains enough velocity, it can just stay around there and will not fall in. But it's the curvature of space-time that want to make it fall, and its mass, the objects having a mass, that just creates this curvature. Some of the big differences from Newton theory is that now this space-time curvature is applicable on anything. Even light, which doesn't have any mass, will still feel this curvature. And that's led to one of the greatest confirmation of Einstein theory. Another consequence is that that deformation of spacetime itself doesn't happen instantly. That deformation, that curvature itself is bound by the universal speed limit of the universe, the speed of light. And so should the sun suddenly disappear, that the curvature that it makes wouldn't suddenly vanish and space wouldn't suddenly become flat again. It would actually move at the speed of light. That effect, the fact that it's not instantaneous, lead to very interesting things. In particular, if I make that little object move fast enough, now the way it's pressing and moving around in that sheet of spacetime, it's actually making everything wobble. And wobble is the technical term. And that wobbling is actually the gravitational waves that I've been talking about at the start. So anytime you have two objects that move in a certain way, they will generate gravitational waves. In order for those gravitational waves to be strong and detectable for us, we need something very large and very massive and very dense that moves very fast. Black hole, it doesn't get any denser and more massive than black holes. And so that's our prime candidates for such waves. If a wave from a pair of celestial bodies orbiting each other, just like in the video I showed, hopefully something massive enough, were to hit Earth, this is what it would look like. Some of you might have seen this video. It still cracks me up every time. But this is the actual effect that a gravitational waves will have on Earth and has had on Earth when it hit Earth. Now, obviously, the scale of the effect is vastly exaggerated for the purpose of this video. Let's actually take a look at some numbers. So human hair is about 0.1 millimeters diameter. An atom is about 1,000,000 times smaller, 10 to the minus 10 meters. And an atomic nucleus is a further 100,000 times smaller, 10 to the minus 15. The actual kind of gravitational waves that the universe constantly throws at us and the ones that we do detect on Earth will change the diameter of the Earth. So this wobbling from the previous video where you saw the Earth being stretched and squeezed in two directions, it will change that dimension of the Earth by about 10 to the minus 15 meters, meaning the entire Earth is moving by about the width of an atomic nuclei. Needless to say, that's not a big deal, and there is no danger whatsoever. Pretty much anything that we do on Earth has a bigger effect than that, which means it's challenging to detect, which is why we get together, which is why gravitational wave observatories is a very international, worldwide effort with a lot of detectors around the Earth. Some of them operational. Sorry, the Kagra detector is just finished the constructions in Japan and is starting to take data. It's now in a finishing its prototyping phase and actually trying to join the more established LIGO, GEO, and Virgo detectors. The GEO detector is the British-German detector, which is much smaller than the other ones and is used by the international community as the proving facility for cutting-edge technologies that we then put into the detectors. But one of the things that is interesting in that field, at least to me, is that all of those detectors there are part of the same collaboration, which shares all of the data, all of the knowledge. The lasers from the LIGO detectors, for instance, were built in the UK. They were tested in the GEO detector in Germany. The suspensions that the detector needs were designed and built in Italy. It's a very fully international effort just because, well, by necessity, kind of, we know this is hard enough that we won't be able to do it by ourselves. And so everybody got together and tried to do it. This is what one of those detectors look like. This is a picture of the Livingston Observatory in Louisiana in the United States. Looks like a building in the center there with two long arms that you can see here, those long beam tubes. They're 4 kilometers long for those detectors. And they try to measure the deformation of space and time as a gravitational wave passes by. So when the gravitational wave passes by, it will deform the Earth, it will deform the meaning of distance, and so the length of those arms themselves will change. By shooting laser beams down those arms, we can measure their length very accurately, and we can see how much it changes as a function of time. This is a quick look inside of the detectors. So at the end of the detectors, you see that picture on the left is the, oops, sorry. The picture on the left is the mirrors that is at the end of one of those arms upon which the laser bounces. You see all of the fairly complicated optics that go into those arms, and the laser at the bottom, which was built in Europe before being sent to the LIGO detectors. It's a pretty powerful laser, but what makes it exceptional for us is it's the most stable laser that that exists. There is a lot of very non-trivial. Sorry for the ghost popping on the side. There is a lot of very tricky engineering that goes into getting this to work, because going back to my analogy from before, 10 to the minus 15, that's the deformation the Earth expects. LIGO is, of course, and Virgo and all the detectors are just a few kilometers in length. So the deformation that they do see, the motions of the mirrors, is more towards 10 to the minus 18 meters over the few kilometers that they see. That's 1,000 times smaller than an atomic nuclei. That's 10 to the minus 8 atom of diameter of an atom. So at those scales, the surface of the mirror is not flat at all. I mean, at those scales, quantum mechanics tells us that we don't even know exactly where the mirror is. So we need to average over a big surface of the mirror. So we send a lot of light on it to, average the position and get a good average. But now that we send a lot of light, we're heating it up, and that deforms it. So we need to hit it the other side in exactly the same way to compensate for it, which is made worse by the fact that we're not just hitting it, because lasers carry energy. They are pushing, they are carrying momentum, they're pushing onto the mirror. So we're actually shining a laser on the other side to push exactly the opposite way, which makes the heating problem even worse. The whole thing is in vacuum, and it's actually one of the biggest and strongest vacuums that exist on Earth. I can go on and on about all of the difficulties that go into these measurements. But the one point, before I explain to you why it's nearly impossible to do it, I want to tell you that it is possible to do it. And the first time it was done was in September 14, 2015, where this is the data that was recorded in the Livingston detector and the Hanford detectors. Some of you will have seen this before. I hope you can forgive me for showing this again. This was kind of a big deal. We had been working on this for 20 years, and then suddenly this is, as a function of time, the deformation of space-time recorded by the Livingston detector on the left and recorded by the Hanford detector on the right. So as a function of time, we could see the arms getting longer and shorter and longer and shorter in those wave-like pattern, where we can actually match those signals with our predicted signals that we can try to compute and see if they match the data, and they do. maybe near perfect match is a bit of a self-congratulatory pat on the back, but it's pretty good. This is an animation to show you all of those different waves of possible gravitational waves, the way we actually go through. So we basically try a bunch of different values. This is, in this example, changing the mass to see what fits, then changing the distance to see what we can fit the data with. And at the end, we apply the sensitivity function of the detectors. So it turns out our detectors are not quite sensitive in all parts of the signal in exactly the same way. And we have to take that into account. And so at the end of this trial and error, we get a signal that matches what we've seen. And this is an example on how we've actually done it for this very first observations, which told us that whatever created the signal was a pair of objects whose total mass was about 65 solar masses, which were at about 410 megaparsecs away from us. In practice, this is not just 2 parameters that we have to fit for. It's 15 physical parameters for the source itself and several hundreds for the properties of the detector that we are fitting at the same time. But for the purpose of this animation, it was easier to shorten things a little bit. So what does this mean? This is a representation of those 2 black holes that we've detected with gravitational waves. I should add that gravitational waves are kind of unique in the way we can actually use them to detect black holes, because, well, black holes are black. And so you can't see them directly with light. Gravitational waves are pretty much the only thing you can use to detect a system like this one, where you have those 2 black holes. One is 29 solar mass, one is 35 solar mass. As far as we know, there is nothing else around. There's no stars orbiting in a funny way where we can infer the presence of a black hole. There's no gas that gets excited by those black holes. But they do emit gravitational waves. Towards the end here, and this is to scale on the orbiting around the UK to get an idea of what we're talking about. The big one was about 35 times the size of the sun. The small one was about 29. They did an entire orbit. So you can imagine the circle around the UK and back in about 0.05 seconds towards the end as they are orbiting. They're actually going, towards the end, they are going at about 60% the speed of light. And the energy that was emitted in the emission of gravitational waves is about 50 times the entire energy output as a peak intensity of the entire universe. What that means really is this is extremely energetic event, and actually those 2 black holes will meet each other and merge and create a bigger stable black hole at the end. If you were to do the math, you might think that this should be a 64 solar mass black hole. It's actually more like a 62 solar mass black hole at the end, because 2 to 3 solar masses were converted into energy almost instantly in the form of gravitational waves. That's a huge amount. I mean, you will be familiar with the E = mc square relation, where the amount of energy is equal to mass times the square of the speed of light. 3 times the mass of the sun is a huge number. The speed of light is a big number. We are squaring it. All of those big numbers together, it's a huge amount of energy that was released. But, and this is what I will slowly conclude my talk with, this was the first one. And because we had this seminar organized for this Saturday, the collaborations, the about 1,800 scientists around 60 institutions worldwide, we made sure that we released our latest catalog of detections on Monday so that I could talk about it today. This is a plot of all of the different black holes mergers that we've detected to date. The first one was in 2015 that I just talked about. This is all of them, and you can see they come in all sizes and shapes. Those are all the black holes. I've removed the neutron stars from it to let you learn about them from the next speakers. But this is all the black holes. Every time that we detect an event, we detect the gravitational waves, we actually get to add 3 dots on that plot. There are the 2 initial black holes, and then there is the one that we know is left over at the end, which is a very neat trick, because that means that compared to our colleagues who are using light to detect black holes, those are the black holes they detected in red, what we call electromagnetic or EM black holes that have been detected by using light and looking at lights from their environments, so stars orbiting them or some other effects that they have. You can see that now we have a bunch and ours are bigger. Not that bigger is better, but it was actually a bit of a surprise that there was so many black holes that were much bigger than the 10 solar mass. So remember when I said at the beginning, 10 solar mass is roughly the average / fiducial mass that we think about when we think about stellar mass black holes. Well, that was true when we could only use light to study them. It turns out that there is a lot of invisible black hole mergers around. There's a lot of invisible black hole collisions which emit gravitational waves, and that we turned a new instrument on the universe, and we were surprised almost right away. And to finish, one small thing that I want to mention, the parameter that we actually measure the best, I talked about the distance between us and the source of the black holes. There is the mass of the 2 black holes. There is actually a particular combination of the masses of the 2 black holes, which is called this Chub mass. This funny combination, the mass of the first black hole times the mass of the second black hole to the 3/5 divided by the sum to the 1/5. That particular combination is very important, and you know it's very important because we gave it a name, Chub mass. It's actually the one parameter that governs the speed of the frequency evolution of the gravitational waves. And that's the one thing that we can measure the best. How quickly the gravitational waves evolve as a function of time. Given how noisy our detectors are, that parameter is our best go-to parameters. And so we tend to refer to events in that sense. Here in the top plot, you can see all of the gray traces are traces of the probability that we gave for that particular parameter, the Chub mass, for each of the events that we've detected. So each individual events here will make one gray trace. There are some that are around 6 or 7 and 9 and 10 Chub masses. Some are around 20, 30, etc. You have all of them. If you combine all of them and you're trying to estimate what is the overall population of black holes that we observed, what makes sense, knowing that we just have a few samples. This is right now, this is done out of the 70 confirmed binary black holes that we've detected using gravitational waves. We can get that distribution. However, something that's important to remember is that big black holes are making big gravitational waves, and big gravitational waves can be detected from much further away. And much further away means that because we live in a space that has 3 dimensions, something that's twice as far away might come from 8 times the volume of space. So we are 8 times more likely to see things that are further away. And so we tend to be a lot more sensitive to the heavy ones than to the light ones. So we need to correct for this if we want to actually know what is the distribution of black holes out there. And this is a result that is very fresh on the presses. This is something that we published on Monday. And so this is the distribution as a function of mass of the population of black holes around. There are a few things that have been interesting and which we will have to work some more on. The first one is the idea of a lower mass gap. From what we've just seen in the talk, core collapse supernovae and type 2 supernovae might lead to an idea that there is a minimum mass for black holes that should be around 5 solar mass, and a maximum mass for neutron star that should be around 2.7 or 3 solar masses, and there should be a gap between 3 and 5. We don't expect to see anything there, or at least one of our theory says we don't expect to see anything there. There are a couple of events in our new catalog that makes us question that a little bit. We're not entirely sure, and we're just at the limit where we can actually make a convincing estimations as to whether the lower mass gap is indeed what's happening or not. We don't quite have just the right statistics. We're just starting to get into it. And seeing how many black holes are around those values will help us refine our models for how supernovae explodes. We also have 3 bumps in this distribution. You can see one around 8.5 chirp masses. There is one around 15 and one around 28 or so. The first one, which corresponds to individual black hole masses of about 10, but chirp mass, which we measure better, at around 8.5, that's almost certainly due to what we call isolated binary evolutions. There are 2 ways to get 2 black holes to get close enough to each other that they will do gravitational waves and merge and make me personally very happy. It's either you had 2 stars that were just born together, and one of them explodes, made a black hole, the other one explodes, makes another black hole, and they stay together, and they just, it's a lovely story. They've all lived together, they died together, and then they have to smash at nearly the speed of light together, as it happens in relationships. But that picture would explain, from our simulations, would explain a peak of black holes at around that value. Another possibility is to have very dense stellar environments, such as globular clusters, where there is a bunch of stars everywhere, explosions happening everywhere, and it's so dense that occasionally enough of them get close together, enough of the black holes that are created get close together that they merge. And this is what we call dynamical formation scenarios. So the fact that we have this bump there might hint to the fact that isolated binary evolutions, the happy partner story of star formation, might be true. I'm keeping it safe by adding question marks in all of those. However, no idea what's happening with those other 2 bumps. We don't know. They are statistically significant. We do see those. Why? We don't really know. And that's exciting. That's job security right there. So we have to actually figure out, what is this? The last feature is what we call the upper mass gap. So another kind of supernovae, pair instability supernovae. There's this fake kind of pair instability supernovae called pulsation pair instability supernovae. And I'm not going to go into details of that at all, just to say that one of the predictions of having black holes created by those is that there should be not a lot of black holes that lead to chirp masses above 50 solar masses. And so there should be a gap. We don't really see that gap, which either means that our supernovae theories are not quite right there, or there are other formation scenarios that dominate, such as this dynamic interactions, which is also a possibility. The point that I'm trying to make with this, and the point that just 1 minute, I swear, this is the end, is that there is a lot still to discover in our universe, in our study of black holes, and that's all. Thank you very much.
Okay.
Sorry, I ran over.
Right. I think what we'll do is we'll have 5 minutes of questions, Phil, and then we'll give people a 10-minute break.
Okay,
Thank
that's
you very much, Vivien.
Indeed. Thank you very much, Dr. Raymond. So we do have a few questions in the chat, in the Q&A. If we don't get to you in this period, I apologize. We will try and answer them by text later in the talk. So the first question from Paul Klein is, how would you describe the difference between a stellar black hole and a supermassive black hole?
Sorry, can you repeat the question?
Sorry, how would you describe the difference between a stellar mass black hole and a supermassive black hole?
I just missed the first bit. The size. So a stellar mass black hole, it has that name because it's of the order of a solar mass, ish. So this is something that we will. I should take a step back. According to general relativity, there are no size limits on either end of the spectrums of what a black hole could be. But given how we can think of ways to form them, we will need to get some. We need to get such a density that really star explosion and supernovae is kind of our main way to create them, except for some very interesting quantum mechanical effects at the initial condition of the universe. But all of those will create black holes between a few solar masses, and the fiducial value is 5, although, as I said, that could change a little bit, up to, let's say, 100 solar masses. Beyond that, we call them intermediate mass black holes because they are a lot more speculative. It's very hard to make them, so they shouldn't happen often. Doesn't mean that they can't happen, but they shouldn't happen often. Supermassive black holes start when we talk about the millions of solar masses. And hypermassive black holes would be the billions of solar masses. Those are black holes that we find in the center of most galaxies. And from a physical point of view, except for the mass number, there are really no differences between all of those black holes. It's what makes black hole science kind of unique in the realm of physics, that they can be fully described by those very few parameters, the mass and how fast they rotate, and potentially their charge, but let's not go there for now. It's a very small number of parameters, and except for the scale, there is actually no difference, to the point where when we make our models and we solve for what gravitational will look like, the total mass of it, that's the free parameters. We can scale it to whatever we want. It's the same thing. It's the same object. So the only difference really is just how big they happen to be.
Okay, thank you. Our next question comes from Irene Rogers. She's asked, in your representation of the effects of an orbiting object on the gravitational waves, the object being orbited was static. What happens to the waves if that object itself is also moving, or also rotating, rather?
Oh, yeah, sorry. That's because, as was mentioned by the previous presenter, as an astrophysicist, I am lazy, and so I didn't bother actually make the middle one move. But you're absolutely right. The middle one will move. It will just move by a little less. And it's the interplay between the motion of the two of them that will actually make those waves. In practice, if one of them is much smaller than the other, while the main one does move, it's so small that it doesn't really affect. This was an example that was supposed to kind of look like something like the solar system. So clearly the sun makes Jupiter, move around, but Jupiter is massive enough that it makes the sun move by about 50 kilometers per hour, if memory serves, which, given the size of the sun, that number is so tiny that it's just that it's hardly measurable even. But technically speaking, it absolutely does move. And the wave does look different depending on how much both of them move, which is exactly how we can tell what is the mass ratio between the two objects. So a wave, it might be 65 solar masses total, but we can tell the difference if it's 60 plus 5 or if it's 32 plus 33.
Okay, thank you very much. I think, Jane, that takes us to the point where we're going to take a short break. So do you want to take over at this point?
Yeah, okay. Thank you, Phil. Yes, we'll try and